Hi, this is Professor Collins. Today we're going to go over some calculations related to stoichiometry. That's the key concept in Chapter 9 of Chemical Equation Calculations. The strict definition of stoichiometry is used to refer to the relationship in quantities between reactants and products according to the balanced chemical reaction. Let's take this reaction here. We know that in order for the law of conservation of mass to apply, we have to write coefficients in front of this product and this reactant in order to have a balanced chemical reaction. We have to obey the law of conservation of mass. What this means in stoichiometric terms is that two of these plus one of these O2 molecules will produce two molecules of CO. In Chapter 8, we learned a lot about the mole concept and quantities related to that. And we could restate this in ways of saying 2 moles of carbon, 1 mole of O2 gas will produce 2 moles of CO. Before we go any further in stoichiometry calculations, let's review the important concepts in Chapter 8. We talked about this conceptual flow where the quantity mole represents Avogadro's number of atoms, or Avogadro's number of particles. That number is 6.02 times 10 to the 23. If we knew how many moles there were of any reactant or product, we could calculate the mass of that reactant or product, finding the molar mass of that particular substance. If we multiply by the molar mass, the number of moles, we would get the mass of that particular substance. Where do we get the molar mass? Well, we get the masses from the individual atomic masses. For example, water, H2O, has a molar mass of 1 plus 16, or 18 grams per mole. If we know the number of moles of reactants or products, we can also calculate the volume of that particular reactant or product at STP, standard temperature and pressure. In order to do this, we would multiply or divide, depending on which direction we would go in this flow concept, by the molar volume. The molar volume at STP is always equal to 22.4 liters per mole. Now, this type of calculation from mole to mass, or mole to volume, or mass to mole, or volume to mole, is crucial for all types of stoichiometry problems that we're going to discuss in Chapter 9. The first type of problem I want to go over is related to the mole to mole relationship. Let's take that same reaction, carbon plus oxygen produces carbon monoxide gas. The balanced reaction was 2, 1, 2. We can state that it takes 2 moles of carbon plus 1 mole of O2 to produce 2 moles of carbon monoxide. But in the laboratory and in the real world, we often don't have exactly 2 and 1 to produce exactly 2. Let's take an example. Let's say we have 2.5 moles of carbon as a solid reactant. And that's the question, how many moles of O2 gas will be required? And how many moles of CO will be produced? We need to apply the molar ratio to solve this problem. First, let's write down the process of problem solving by first writing down what we're looking for. The number of moles of O2. We're starting with 2.5 moles of carbon. How do we get from this number to this number? Well, we apply a unit factor that is the ratio of O2 to carbon, which is 1 mole O2 for every 2 moles of carbon. And you see here that the moles carbon cancel, and the unit that's left in your answer is the one you're trying to find. The final answer is going to be 1.25 moles of O2. So if you have 2.5 moles of carbon, you're going to need 1.25 moles of O2 to react with that. And how much CO will you produce? Well, let's start over. If we have 2.50 moles of carbon, we want to find the number of moles of CO. We multiply this time by the unit factor of this ratio, 2 to 2. There's 2 moles of CO for every 2 moles of carbon. This is a solid, by the way. The units moles carbon cancel, and you have, not CO2 rather, another typo. The ratio was 2 moles of CO for every 2 moles of carbon. Obviously, you get the same number of CO produced as you started with carbon in the reactant side. If you read the chapter or reviewed the lecture that I built the audio file out of, you'll know that there are 3 types of stoichiometry problems. The first type is called mass-to-mass stoichiometry. The second type is mass-to-volume. And the third type is volume-to-volume. Here is a mass-to-mass stoichiometry problem. By mass-to-mass, I mean, for example, I have a mass of 1.25 grams of mercury oxide in this decomposition reaction. And I want to know how many grams, or what is the mass of mercury produced. And of course, the first thing you do in all types of chemical equation calculations is to make sure you have a balanced reaction. Well, in order to do this, I have to first put a 2 over here so I have my oxygens balanced. But in doing so, I need to put a 2 here. So for my stoichiometry for this reaction says 2 moles of this will react with 2 moles of this to produce 1 mole of this. Well, I don't have 2 moles of this. I only have 1.25 grams. The 3-step process to do a mass-to-mass stoichiometry problem involves converting the mass of what you're given to the moles of what you're given. That's step 1. Step 2 means apply the stoichiometric ratio to determine how many moles of the product you should produce. Then when you know the number of moles of the product, you can convert that back to the mass of the product. Now here you will use the molar masses twice. Once for this substance and once for this substance. So as I said, a 3-step process. In the first step, I'm going to take the mass of what I'm given, 1.25 grams of mercury oxide. I'm going to divide that by the molar mass of mercury oxide. How do I get that? Mercury has a mass of atomic mass of 200.6. Oxygen is 16.0. So 200.6 plus 16 is 216.6, or 216.59 to 5 significant figures. That's the molar mass of mercury oxide. I divide by that because I want my units of grams to cancel. And after the first step, I've converted the mass to the number of moles. When I divide the mass given by the molar mass of this material, this substance, I get an answer of 0.00577 moles of mercury oxide. In the next step, I'm going to apply the mole ratio of mercury to mercury oxide to get the number of moles of mercury. The second step is pretty straightforward because the ratio turns out to be 2 to 2 or 1 to 1, and your unit factor is 2 moles of Hg over 2 moles of HgO. So it turns out you have the same number of moles produced as you started with. But we didn't start with 2 moles when we started with 1.25 grams. So after the first step, we determined the number of moles of HgO, applied step 2, the mole ratio, to get the moles of Hg. In the last step, though, we want to determine the mass of Hg. We're going to take the number of moles, multiply it by the molar mass of Hg, of mercury. In the last step, I take the number of moles of mercury that I calculated after step 2, multiply that by the molar mass of mercury to get the mass of mercury in grams. Now note my units cancel appropriately. Moles in moles in the numerator and denominator, so all that's left is grams in my answer. This is a mass-to-mass stoichiometry problem. If the mass of the reactants equals 1.25 grams, and I calculated the mass of this product to equal 1.16 grams, let's apply our understanding of the conservation of mass to determine what the mass is of oxygen. Well, I could do it two ways. I could do another three-step stoichiometry problem, starting with this, or even starting with this. I would start with this, divide that by the molar mass, just like I did here. Then I would apply the mole ratio, which is slightly different, and then I would multiply by the molar mass of O2. But a simpler way, in this example at least, is to apply our understanding of conservation of mass. Matter can either be destroyed or created. We know the mass of the reactants has to equal the mass of the products. Well, I simply subtract 1.25 minus 1.16, and I get the mass of the oxygen, which is easy enough to determine, 0.09 grams of O2. So on the left, you have 1.25 grams. On the right, you have the mass of this product plus the mass of this product. That plus that equals 1.25. Let's look at another mass-to-mass stoichiometry problem with this reaction. Here is a balanced reaction of potassium iodide and mercury nitrate to produce mercury iodide and potassium nitrate. Now it's balanced in the sense that you have 2 moles or 2 molecules of potassium iodide reacts with 1 mole or 1 molecule of mercury nitrate to produce 1 mole of mercury iodide and 2 moles of potassium nitrate. I'm leaving off the phases to simplify the calculations or to make it more clear. In this balanced reaction, you see our stoichiometric ratios are 2, 1, 1, and 2. Let's solve this problem. How much potassium iodide, I'm going to write a question mark here. If I'm asking for the mass, that means how many grams of potassium iodide will I need if I do a reaction and produce 1.78 grams of mercury iodide. Now this is a similar type of mass-to-mass problem as the previous one, and we solve it the same way, and it doesn't matter if we're going from product side to reactant side or reactant to product side. Given this one number, I can determine the masses of this reactant and this product in this balanced reaction. In the first step of this 3-step process, I want to take the mass of what I'm given, that's mercury iodide, 1.78 grams, divide that by the molar mass of mercury iodide. I get from the periodic table that tells me that mercury has a mass of 200.6. Each iodide is 126.9. You have 2 of them. So the molar mass of mercury iodide is 454.39 grams per mole. I need to divide so that my units of grams cancel and I get mole in my answer. So after the first step, I determine the number of moles of this product, which is 0.00392 moles mercury iodide. In the second step, I want to convert that number of moles of mercury iodide into the moles of potassium iodide, because that's what I want. And what is this ratio? There's 2 moles in the balanced reaction of Ki, potassium iodide, for every 1 mole of mercury iodide. When I write the unit factor like this, the units of moles mercury iodide, that should say moles there, will cancel. So after this step, I've calculated the number of moles of potassium iodide. In the third step, I'm going to convert the number of moles of potassium iodide to grams of potassium iodide. After step 2, after multiplying the number of moles of what I started with by the mole ratio of potassium iodide to mercury iodide, which is 2 to 1, I get twice as many moles, or 0.00784 moles of potassium iodide. In the third step, I'm going to take the number of moles of potassium iodide and use the molar the molar mass of potassium iodide multiplied by the molar mass to get the mass of potassium iodide. That's the final step of this mass-to-mass stoichiometry problem. In the last step, I take that number that I calculated after step 2 for the number of moles of potassium iodide, 0.00784, multiplied by the molar mass of potassium iodide. That's K, which has a mass of 39.1, plus iodine of 126.9. Add those two together, I get 166.0 grams per mole. When I multiply those two numbers together, the numerator of the moles Ki and the denominator moles Ki cancel, and I get a final answer of 1.30 to 3 significant figures grams of potassium iodide. I can go up to my reaction here and say I need 1.30 grams of potassium iodide with a certain amount of mercury nitrate to produce 1.78 grams of mercury iodide. The next type of stoichiometry problem we're going to look at is called the mass to volume stoichiometry problem. It's very similar to mass, except instead of going from grams to grams, we're going to go from grams to volume in liters, grams to liters. Or I could go from liters to grams. It involves the same similar three-step process as mass to mass, just that one of the 3 steps, instead of using the molar mass, we'll use the molar volume. And let's look at this example. Sodium azide, which is a compound used in car bags that blow up when you hit a bumper or a wall or another car. What happens in the airbag is that a spark ignites this powdered sodium azide and produces a lot of nitrogen gas and some sodium metal. The gas, of course, is what fills up the airbag very quickly. This is the balanced chemical reaction for this reaction, and to obey the conservation of mass principle, it says that 2 moles of this plus 2 moles of this will produce 2 moles of this and 3 moles of nitrogen gas. Let's solve this problem. If we start out with 100 grams of sodium azide in a car safety airbag, how many liters of gas will that produce? Now let's keep in mind, we can only use molar volume of the value that we're familiar with if we're working at STP. And I'm going to write that caveat up here. At standard temperature and pressure, there's always 22.4 liters per mole of any gas. So the process is very similar to mass calculations. First, we're going to take the mass of the reactant that we're given, 100 grams of sodium azide, divide by the molar mass of sodium azide, which is 65.02 grams of sodium azide per mole of sodium azide. I get that by adding the mass of one atom of sodium, that's 23, plus 3 nitrogens, which is 14, 14, 14, and 23 equals 65.02 to 4 significant figures. When I do the calculation, 100 divided by 65.02, I get 1.54 moles of sodium azide. The next step, step 2, I want to apply the mole ratio of sodium azide to nitrogen. That's 1.54. In this particular reaction, moles of sodium azide, taking the number resulting from step 1, divide that by the mole ratio, which is going to be 3 to 2. There's 3 moles of N2 for every 2 moles of NaN3. Again, as you should always write the units down so you can see what cancels appropriately. Moles of sodium azide will cancel from the numerator and denominator. So after step 2, you now know how many moles of this product you have. After multiplying the moles of NaN3, sodium azide, by 3 over 2, which is the mole ratio of what I'm looking for over what I started with, I get 2.31 moles of N2 gas. And then the final step, of course, is to do something differently here than we do in mole-to-mole types of calculations. Multiply the number of moles of N2 that we calculated times the molar volume of N2, which is equal to 22.4 liters of N2 per mole of N2 at STP. That changes with temperature and pressure, but at standard temperature and pressure, it's always 22.4. My units of moles N2 cancel, and my final answer, I get 51.7 liters of N2. Now, it's interesting to think about because that's over 50 liters is over 10 gallons of air into gas, relating that to English units. 10 gallons of air that would go into a small airbag. That's what protects you when sodium azide is converted to sodium and nitrogen gas. This is a mass to volume problem. The third type of stoichiometry problem is a rather straightforward one called the volume to volume stoichiometry problem. It only requires one step. That's if we're at STP or other types of constant temperature and pressure, no change, and I'm going to put R constant. We'll learn more about this when we study gas laws in the next chapter. But volume to volume stoichiometry problems require only one step, the middle step, which is the mole ratio application. That takes place, that applies if you have standard temperature and pressure, STP, or if temperature and pressure are constant. So let's take this example. If you have 5.55 liters of nitrogen gas in this gas between nitrogen and hydrogen to make ammonia, in fact, this is the commonly used in industry for the production of ammonia, is the reaction with nitrogen and hydrogen gases. But in our calculation practice, let's try this example. 5.55 liters of nitrogen. How much ammonia will I produce in terms of the volume? A volume to volume calculation. Very straightforward. If we have 5.55 liters of N2, I simply want to multiply by the mole ratio of ammonia, which is 2 moles of ammonia for every 1 mole of N2. Which means if I start with 5.55 liters of N2, I'm going to produce 5.55 times 2, or 11.1 liters of ammonia gas. Let's take this problem one step further. If I start with 5.55 liters of nitrogen gas, I will produce 11.1 liters of ammonia. But how many liters of hydrogen gas will I need to make this reaction go to completion? Well, again, 5.55 liters of nitrogen. My mole ratio is slightly different. It's 3 to 1. There's 3 moles of H2 for every 1 mole of N2, which means I'll need 16.7 liters of H2 gas. Now you might want to ask the question, why doesn't this number plus this number equal this number? If we had reactants and products in units of grams, that would have to apply, right? Because the law of mass, the law of conservation of mass tells me the mass on the reactants equals the mass on the products. Well, that's not the case necessarily with gases. Obviously, 5.55 plus 16.7 does not equal 11.1. I'm going to do one more type of stoichiometry problem that includes this concept called limiting reactant. The limiting reactant, by definition, is the reactant. Which of these? One of these is the limiting reactant. One's the excess reactant. The one that is the limiting reactant, either this or this, determines how far the reaction goes. When you think about that, that means whichever of these has the smallest amount of quantity to produce the amount of product, so when the product stops, that's the so-called limiting reactant. Let's put some numbers with this to further define that concept. We know that if we have 50 grams of this reactant, manganese oxide, we could do a 3-step stoichiometry, mass-to-mass stoichiometry problem to determine how many grams of this product we will produce. But as happens in the laboratory and in the real world, we don't always use those stoichiometrically correct amounts of reactants and to produce products. So for example, if we have 50 grams of this reactant, manganese oxide, and 25 grams of this reactant, one of these, which one of these will be in excess, how many grams of manganese do I really produce? What I need to do is determine which of these two reactants is my limiting reactant. So in any type of stoichiometry problem, the very first thing I have to do is have a balanced chemical reaction, don't I? And to do this, I need coefficients of 3 here, 4 here, 3 here, and 2 here. Now I have 3 manganese atoms on both sides, 6 oxygen atoms on both sides, and 4 aluminum atoms on both sides. Now I have a balanced chemical reaction. In order to determine which of these is the actual limiting reactant, I have to do 2 different stoichiometry problems. I have to do 2 mass-to-mass stoichiometry problems involving 3 steps each. First, I'm going to do a problem assuming MnO2. I'm going to say if MnO2 is the limiting reactant, I'm going to have 50 grams of manganese oxide. How many grams of manganese will that produce? Then the second 3-step second 3-step stoichiometry problem will make the assumption if aluminum is my limiting reactant. So I would have a 3-step problem where 25.0 grams of aluminum will produce how many grams of manganese oxide. So once again, let me show you the setup. For the first 3-step calculation, mass to mass, I'm going to put my finger over this number here. I'm going to determine how many grams of manganese is produced if I start with 50 grams of manganese oxide. 3-step stoichiometry problem. Then in the second part, I'm going to put my thumb over this number. I'm going to say, what if aluminum's a limiting reactant? I have 25 grams of aluminum. How many grams of manganese will I produce? When I'm through my 3-step processes, I'm going to determine how many grams of manganese is produced if this is a limiting reactant. And then I'm going to do another 3-step calculation to determine how many grams of manganese is produced if aluminum is my limiting reactant. These will be different numbers. Which one's correct? Well, the correct one is the one that produces the smallest amount of mass, the smallest number of grams of manganese. Okay, I'm going to cover the second part just to illustrate how we calculate first the mass of the unknown product, starting with the mass of manganese oxide. I'm ignoring this number here for now. So 50 grams of manganese oxide, first step, divide by the molar mass of manganese oxide, 1 manganese atom plus oxygen plus another oxygen to get A 6.94 grams per mole. Units, grams cancel. The second step, I multiply by the mole ratio of manganese to manganese oxide, which is 3 to 3. These units would cancel, moles of manganese oxide. And the third step, I want to convert back to the mass of manganese produced, if this is my limiting reactant, and I multiply by 54.94 grams of manganese per mole of manganese. That's if I'm using a periodic table that has 4 significant figures, the one that you would get on exams or have been getting on exams has manganese, a mass of manganese to 54.9 to 3 significant figures. That's okay to use this one as well. When I do that, I get an answer of 31.6 grams of manganese. All right, I'm going to put a circle around that for now. And then go to my second possibility. Again, I have this reaction where I have 2 different amounts of reactant. On this second part, I'm going to ignore this number here and start with 25 grams of aluminum to determine if it's a limiting reactant. First, in my 3-step process, I divide by the molar mass of aluminum, which is 26.97 grams per mole, to 4 significant figures. Once again, on our periodic table, it says 27.0 to 3 significant figures. Either value is correct, but here I'm going to use 4 because I used a different periodic table which had more significant figures. That's the first step. I convert that to moles of aluminum. The second step, apply the mole ratio of a manganese to aluminum, which is different. It's 3 to 4 manganese to area aluminum. In the final step, as I did in the previous example, I multiplied by the molar mass of manganese, which is 54.94, to determine how many grams of manganese. And when I do this, I get 38.2 grams of manganese. So 2 3-step mass-to-mass calculations, 2 different numbers. Which one's right? Well, remember, I said the lowest number is going to be the correct one. So I'm going to put an X through this number. The lowest number is the correct number representing the amount of product produced. It also tells me that manganese oxide is my limiting reactant. Now let's think about that. We started with 50 grams. The reaction takes place when you add aluminum and heat. When you produce 31.6 grams of manganese product, that reaction stops. You've converted all that. As it turns out, you had an excess amount of aluminum. If aluminum had been a limiting reactant, we would have produced more. So this is the way to determine what the actual limiting reactant is. In this case, I'm going to put Lr above manganese oxide in this equation. And I'm going to put excess, XS, this is the excess reactant. Not all of this is going to be used. It's going to be some number less than 25 because it's there in excess. How much less? Well, we could easily find that out, couldn't we? Because if we know this is a correct number, we could do a 3-step mass-to-mass stoichiometry problem to determine what that is, how much of that actually is. And it turns out to be some number less than 25 grams. That's the concept of limiting reactant shown in this type of problem where you have to do 2 separate 3-step stoichiometry, mass-to-mass stoichiometry problem. The last concept we want to discuss problems with in this chapter is a concept called percent yield. As it turns out, in laboratory experiments in chemistry classes, and when chemistry is done in the real world, for example, to make ammonia gas from sodium and hydrogen, reactions don't always go to 100% completion. And when they don't, what we can do is calculate what amount of that actually did get completed. That's called the percent yield, and it can be calculated as shown in this following example. Let's look at this example of a reaction and to illustrate percent yield. This is a similar reaction to one that we actually do in the laboratory. We do an experiment where we measure out 3.00 grams of sodium bicarbonate, and we want to determine how many grams of sodium chloride is produced. Now, as you can see, we have a mass of reactants we have a mass of products that we're going to determine. We spent a lot of time talking about mass-to-mass calculations. If I were to do a 3-step mass-to-mass calculation of sodium bicarbonate to sodium chloride, I would do 3 steps. In this process, I'd take 3.00 grams, divide by the molar mass of sodium bicarbonate, multiply by the mole ratio of sodium chloride to sodium bicarbonate, which happens to be 1:1. This is a balanced chemical reaction. And then I would multiply by the molar mass of sodium chloride to get the mass of the sodium chloride. If I do this with my calculator in the 3-step process, the theoretical mass that I should get would be 2.01 grams, starting with 3 grams of sodium bicarbonate. 2.01 grams, I calculated with the 3-step process. This is my theoretical yield. In theory, if I start with 3 grams of this, I'm going to get 2.01 grams of this. But let's say I do an actual experiment like we do in the laboratory at FSCJ, and I come up with my experimental amount of 1.98 grams. For some reason, I have a little bit less than I should have gotten in theory. Therefore, what is my actual percent yield for that particular experiment? Well, in this example, the actual yield is my experimental yield, 1.98 grams, divided by the theoretical yield, which is what I calculated I should have gotten in theory. If things go 100% perfectly well, which we know that never happens in the laboratory, or doesn't ever really happen in chemistry in the real world, we should produce 2.01 grams in theory. This number divided by this number times 100 equals my percent yield. In this example, I would get a percent yield of 98.5%. That means 1.5% of what I should have gotten in theory did not happen for one reason or another, and that's quite common. Experimental reasons, perhaps I had some extra unreacted sodium bicarbonate. There's a lot of reasons. And that concludes the calculations for Chapter 9.